Okay, let's take a look at project number 6. Project number 6 continues in our series of GPU-based projects. This one is using OpenCL. OpenCL runs everywhere, and that's its big advantage, is it runs on NVIDIA and AMD and Intel. It even runs on Intel and AMD CPUs, not just GPUs, and it runs on FPGAs. So you'll see OpenCL in use in the industry whenever you have something that needs to run everywhere. Okay, it is different from CUDA. You do your programming in two files, one CPP, one .cl. They get compiled separately, and the compiler for the .cl is in the driver, is in the OpenCL driver, and so you don't have to provide a separate compiler. And that's probably the reason they did it this way, is you can use unmodified G++ to compile the CPP. You can use unmodified, unenhanced Visual Studio to compile the CPP. But anyway, how you choose to do this is up to you, and I will show you, me attempting to run it live in this video. All right, warning, warning, warning. The flip machines do not have GPU cards in them. OpenCL will not run there. You can probably compile there. We put the compilers there. G++, of course, is there, but it does not have any GPU cards. So don't try and run it. If you run it, you'll get some very weird, uninformative error message. But what it really means in English is, I can't run this. Okay, Rabbit has a GPU in it. I recommend you do your developing and debugging on Rabbit because you can just run the program. Okay, and the DGX, it's a batch system. You have to submit it, wait for it to come back, and all of that. But Rabbit is a great place to be doing developing and debugging. Okay, and if your own system has a GPU and has the OpenCL drivers loaded, then feel free to use that. And in the stuff you should be interested in, part of the class resources page, there's that program print info. That's really how you can tell if you've got OpenCL supported, is you run that print info. And if it runs, yes, you have it. And if it doesn't run, no, you don't. But you can go get it and install it. But anyway, yeah, you can run it on your own system. All right, so introduction to this project. We're going to do a regression. Basically, we're producing from an X or a set of X's and Y's, we're producing Y equals MX plus B. We're doing a linear least squared regression. We will be computing M and B. Okay, here is skeleton code. Yep, there it is. And there will be question marks through here somewhere. There we go. There's some question marks. So yes, don't just compile it and then wonder why it's not compiling. It has question marks. Here's a skeleton of the .cl. If you click here, the browsers don't know what that is. It won't show it to you. It'll try and get you to save it, which is good. But if you click here, you can see it. And oh, look, there's question marks in here as well. These are the arguments to the GPU function. And one of the things I do, which is confusing to some, is I pound define in as nothing and pound define out as nothing, which lets me label the arguments, whether they're coming in or going back out, without causing any harm, because in the preprocessor, these just become nothing. That's what those are doing there. All right, so you're going to read a data file. The data file has 4 million XY pairs in it. However, you're going to try different data sizes. So, basically you're going to read the 4 million XY pairs, but you're only going to analyze some of them. Okay, not all of them. So yes, you are going to change data size to do smaller than 4 million pair arrays. You're going to create an X array and a Y array and pass them over to the GPU. In order to do that linear regression, your GPU program is going to do this. It's for every XY pair, well, it's summing up all the X squareds, all the X's, all the X times Y's, and all the Y's. Yes, this is what you need for linear regression. I would be happy to show you why that is the case if you would like to see it sometime. Okay, but I'm not going to put it here. Okay, so the GPU program is going to do this for each XY pair, and then it's going to return that array of those values back to the CPU, and the CPU is going to sum them up. We're not summing them in the GPU. We could do a reduction, but we're not summing them in the GPU because, well, the GPU's different work groups can't talk to each other. So we're going to sum them on the CPU. Okay. We're going to vary two things. We're going to vary the data set size, and we're going to vary the local size. That's the number of threads per block. Okay, and I'll show you some possible ways of doing that. Once you get all of these back and you've summed them in the CPU, there's a function that you're given in the sample code that will solve for M and B. Okay, and you're going to report the M and B you got just to convince us that you did it correctly. Like so many other projects, you're going to do two graphs. Well, you're going to turn your numbers into a pivot table, into a rectangular table, and then do two graphs from that. And you're going to do a PDF report. Okay, this is how you use the solve. And again, this is in the sample code. Developing this project, if you are on Linux, like you're doing this on Flip or on Rabbit, or I guess not on Flip. Well, you can compile on Flip. You're going to need these 2.h files, so just right-click here and save them. And if you're on, say, Rabbit, this is your compile sequence. Here is where, at least on Rabbit, we are saving the OpenCL library. So it is there. And then you just run it. If you're on the DGX, you need to do that batch file. And here is a way you could do it. And I put in the whole for loops in here because if you're going to batch submit, if you're convinced it works, if you've debugged it on Rabbit and now you're convinced it works, you might as well just run everything in one swoop. So there you go. If you're on Visual Studio, say on your own system, grab this zip file, unzip it, and you should have everything you need there. And there is a OpenCL library that's included there and already linked in. You should be able to just double click the SLN file and off you go. In the sample code, there is a function to figure out what platform and device number you should be using. One of the great things and complicated things about running OpenCL is because it runs everywhere, it's quite possible that you would find on your own system 1, 2, maybe even 3 different things that are capable of running OpenCL. And so you really want to run on a GPU, a powerful GPU, but the CPU might show up in that list. That function it's called select OpenCL device, and you can look at it because the source is there in the sample code. It's right there. So you can see what its logic is, but it's looking for a GPU card. And then it's going to do that. And there's a print statement in the bottom of it that says, oh, okay, after analyzing all you've got, I've chosen this platform and device. Yeah, you can use that. It's interesting to look at. You probably eventually want to comment out that print statement so that it doesn't get into your CSV file. On Rabbit, this is what it printed out, which we deliberately didn't install the OpenCL drivers for the Rabbit CPU because we don't want you to accidentally use that. Your performance would suffer. Okay, here we go. Performance table. Yep, that rectangular table you're used to seeing. 2 graphs. and tell us what the M and B values are in the linear regression. And here's the commentary. So yes, that's how the points will be assigned. All right, let's throw caution to the wind and try and run a live example. So here we are. We're over here on Rabbit. And if I run my makefile, click, yep, there we go. And then if I say run regression, oh, darn, it didn't print out the correct M and B. Yep, sorry, you have to figure that out for yourself. But it did run 4 million values, and it used a block size of 8 threads per block, which from our discussion of GPUs, is really not that good because there's a minimum. You really should run a minimum of 32 per block. But even with 8, which is like crippling the yellow robot, we still got over a billion of these points handled per second, almost 2 billion. So yeah, we're looking pretty good here. All right, now we're really going to throw caution to the wind, and we will go over on the DGX hpc.engr.oregonstate.edu. Yep, there we are. There we are. CD to wherever you keep your stuff. Okay, so now we are over in the same folder we were over on Rabbit a moment ago. If I do an ls, we can see that we have a file called submit.bash. And it looks like this. So here is the 2 nested for loops. Here we're doing several different numbers of threads per block. Here we're doing several different sizes of the data file. And here we're running it. Okay, so remember, you have to start with module load slurm. Love that word, slurm. Okay, now we should be able to say sbatch and submit dot bash, and there we go. And at this point, if I do an ls minus lt, that is, t is what's the most recently modified. Oh, look, it is filling up regression.err. What I like to do is run the Linux tail minus f regression.err. This will just keep showing me what it's printing. And so here we go. And so for a million with 8 threads per block, we're getting 1.3 billion per second. And with more threads per block, we're getting more. And as we go up bigger data set sizes, yeah, look, we're up here at 5 billion, 6 billion. Yeah, it is very sensitive to data set size. The more data you throw at it, the better the GPUs are. It takes a lot to saturate the GPUs on the DGX system. And there you go. And tail minus F will just wait forever for more things to show up in the file. So once it gets to the end of everything, hit Control C. So when you've computed M and B, you probably want to just write them down and then comment out that print line, because if you comment out that print line, then what you have here is a very nice CSV file. And so you could take that, I could say copy regression.err to regression.csv. And now I just double click on the CSV file if those M and B lines are not in there. So you can delete them by hand, or you can just take them out of the print. But This is Project 6. This is how to run it both on Rabbit and on the DGX. So have fun. I'm excited to see what you do with it.